Hello everyone, my name is Pedro Navarro and I'm part of the Blentech team, and today I'll be giving a presentation on vacuum cooling and how it relates to the food manufacturing industry. Before I get started on the presentation, I did want to outline some of the applications of products where Blentech has experience and has also had success with vacuum cooling for those of you who have not been exposed to the vacuum cooling technology. This includes, but is not limited to, ready-to-eat meals, prepared meals, vegetables and fruits, meat, poultry, and seafood, sauces, spreads, fillings, and pet food. All these applications benefit from vacuum cooling's fast and even cooling and does a great job of maintaining product integrity. Before I get too far along, I just want to take a step back and establish some definitions so that we know exactly what vacuum actually is. A vacuum can be defined as any space with below atmospheric pressure. Not sure if you guys recall from your chemistry class or physics class, but while we are sitting in a room, we are subject to 14.7 pounds per square inch on our body. This changes based on elevation, and as you guys have all heard, the classic example of boiling water. In Chicago, if I go to boil a pot of water, the temperature of water will boil at 100 degrees Celsius since we are roughly at sea level. However, if you take that same pot and go to Machu Picchu, that same water will boil at 92 degrees Celsius, and that's because at Machu Picchu at a higher elevation, therefore subject to lower atmospheric pressure. This next slide shows the relationship between boiling temperature and pressure. As you can see, as you get closer to absolute vacuum, your boiling temperature basically falls off a cliff. And the example I always like to give, because it's sometimes easy to just talk about theoretical, is when I was at a startup about 2-3 years ago in Canada, we had a 5,000-pound cooker and we filled it with water. As I was trying to identify the leakages, I spent about an hour and just tightening up and fixing all the loose fittings. And when I was done, I ended up opening the cover and basically the whole water was frozen, as you can see from this image. So this just kind of shows the power of vacuum cooling, and it does work. This picture does a good job of showing it. So you may be asking, how does this work? Why does water boil at lower temperature under vacuum? At a high level, when boiling water, the vapor bubbles are being prevented from exiting because they are being pushed down by atmospheric pressure. However, once the atmospheric pressure is less than the vapor pressure of the bubbles, that is when vapor can be released, and at that exact temperature is what we call the boiling temperature. So why does this matter in the food industry? The reason this matters in the food industry is because when you pull vacuum, you essentially cool the product. The evaporation process absorbs heat from the product, causing it to cool quickly and evenly. The example I always like to give is sweating. When you sweat in your skin and it evaporates, the heat from your skin is used as energy that removes energy from your skin and in turn makes you feel cooler. Here's a phase diagram showing the different phases of water as it goes from solid to liquid to gas. From the liquid to gas stage, what we call latent heat vaporization, it takes that certain amount of energy to go through that phase change, and that removal of energy is what causes the heat from the product to be removed and in turn cool your product. Now I would like to pivot to the different types of vacuum equipment we use at Blentech. We use ejectors, liquid ring vacuum pumps, and also what we call a hybrid system, which is essentially a combination of the two. I'll go over how they both work, or how they all work, and how we use them. Steam ejectors are one of the first types of vacuum systems that were used, and it's mainly because of their simplicity, no moving parts. You apply high pressure motive medium, in our case steam, and push it through an ejector, and that in turn causes a Venturi effect. The classic example is of the one smoking a cigarette in a car. I'm sure you guys have all seen this happen, but if you're smoking a cigarette in a car with closed windows, the moment when you open the window, the high velocity draft causes smoke in the car to be sucked out of the car. And the simplest way to explain that is how the Venturi effect works. The ejector is typically paired up with a condenser, and that condenser, as the steam goes through it, is brought down back to a liquid state, and that helps form a deeper vacuum as the volume of the steam reduces drastically and helps achieve a deeper vacuum. So now I'm going to show a video of how a steam ejector works.
Steam ejectors use a motivating fluid and pressure to velocity energy conversion to create vacuum. Nozzles convert high-pressure steam to high-velocity steam in the mixing chamber to create a low-pressure region. As the steam and entrained air travels down the diffuser, kinetic energy is lost and pressure increases again. Steam ejectors handle high volumes of gases including wet, corrosive or particulate-laden vapors and operate in the rough or medium vacuum range with operating pressures to 3000 TOR. Multiple nozzle designs improve efficiency. Steam ejectors' low maintenance design has no moving parts and can be mounted in any orientation. Multi-stage systems offer improved vacuum and may contain up to 6 ejector stages. The number of ejectors is determined by the level of vacuum required. Condensers are included to remove steam from the system and reduce load on the later stages. Shell and tube condensers, such as the one shown here, cool the steam down using arrays of cooling tubes. Condensate is drained from the system, allowing more steam to be added at the next ejector. Each system is a design, and multiple condensers can be used as well. Steam ejector systems provide the lowest capital cost among vacuum process pumps.
All right, now changing gears to liquid ring vacuum pump. So basically, the liquid ring vacuum pump is a mechanical pump that has an eccentric rotor that as it rotates, it creates an eccentric liquid ring, hence the name, and that ring is able to create pockets of air and expel them from the system, creating a vacuum. It's a simple technology that's heavily used in the industry. Now you may be asking, why liquid ring vacuum pump instead of other vacuum pumps? The reason why Blentech uses liquid ring vacuum pumps instead of other vacuum pumps is because they're able to tolerate steam and moisture without damaging and also reducing efficiency. Other vacuum pumps, such as dry pumps or dry screw pumps, do not do well with handling moisture. It's also able to purge the system of non-condensables such as air and process gases while providing a smooth, stable vacuum. And in general, it is a robust design with few moving parts. So now here is a video showing a vacuum pump in operation. So now moving on to a hybrid system. As you can see from the image, there are multiple ejectors, condensers, and also a vacuum pump. The reason why they are paired is because they rely on each other's strengths. In our vacuum system and the way we operate it, we start off using the vacuum pump, but the vacuum pump alone cannot achieve a very deep vacuum, but it's efficient in getting down to deep enough level. Then when you pair it with a steam ejector, we're able to take it down to a much deeper vacuum required for the process, required for whatever process timing or also whatever temperature you're trying to achieve. This is a much more efficient process because it takes into account the pump's efficiency while also taking into account the ejector's ability to get to a deep vacuum. Now here is a video of the hybrid vacuum system.
Rotajector systems were developed by Kroll-Reynolds vacuum engineers in the 1970s to address rising energy costs. Rotajector systems are high-efficiency combination ejector liquid ring vacuum pump systems, wherein the liquid ring pump replaces the final ejector stage of the system to reduce steam consumption. Rotajectors are highly reliable with only one moving part. They handle a wide range of gases, vapors, particulates, and contaminants without the need for filters, separators, or traps. The processed gases to be handled by the rotojector system are drawn in through the suction inlet of the first stage ejector and compressed by the ejector stages to an interstage condenser. The interstage condenser cools the gases and condenses the vapors, reducing the load to be handled by the liquid ring vacuum pump. The liquid ring vacuum pump serves as the final compression stage. The condensate from the interstage condenser drains directly into the pump suction port. Pressurized steam is required for operation of the ejector stages, and a continuous flow of sealant water and electrical power is required for operation of the liquid ring pump. The liquid ring vacuum pump is designed to replace the final ejector stages, thus reducing steam consumption. Rotojectors can be installed at ground level, eliminating the need for barometric condensate piping. Rotojectors can be operated using low-pressure steam, eliminating the need for high-pressure boilers. Each rotojector system is custom designed, with the liquid ring vacuum pump size optimized to match the ejector design.
So as you can see from this image, basically this is our common setup. A machine, as you can see here. Then there's ducting, a knockout pot, which the knockout pot is used to separate any particulates from the vapor, and then the vacuum system. Most customers, what they end up doing whenever they decide to go with a vacuum system is they have the idea of pairing it up with two machines. And the reason for this is because you're able to cook on one and cool on the other, and then alternate as you needed. However, you cannot just turn on the vacuum system and expect to work on your product. And I've witnessed this firsthand. If you decide to apply all these technologies on a batch of product, more likely than not, you would suck all the product into the duct, knockout pot, and worst case scenario, you would end up into the vacuum system with very little product in your machine once you're done with the process. Blentech has developed a proprietary algorithm that is able to run in a controlled manner and be based on recipe parameters that are dependent on your product and give you consistency that you need on every batch. So the next question comes, why does a vacuum system make economic sense? Just on a high level, the cost benefits of using a vacuum system as opposed to other cryogen technologies are pretty evident when it comes to utility costs. Obviously, with a vacuum system, there's a lot higher capital costs in order to get it up and running because you need to purchase a vacuum system as well as a chiller. But however, once you get it in operation, the utility costs required for the vacuum system are much lower, as you only need water, steam, as opposed to expensive cryogen cooling mediums. And you can see here, it's just kind of a high level representation of the two scenarios using CO2 versus a hybrid vacuum system. You can see that when you use CO2 to cool a 5,000 pound batch from 180 degrees Fahrenheit to 40 degrees Fahrenheit, the costs are in the millions per year, depending on the batches that you end up doing, versus with a hybrid vacuum system, the costs are in the hundred thousands. So overall benefits of a vacuum system include it's just gentler on product, less mechanical work, because as you guys are aware, whenever you add cryogen, you have to do a lot of mixing, which essentially causes a lot of shear on your product. And also the other risks that are included are freezing of product and uneven cooling, because sometimes when you add cryogen, it forms ice balls within your product. The other benefit, and something that I've witnessed firsthand, is the uniform temperature distribution. The entire batch cools evenly, not just on the surface or not just in certain pockets. Also, as I mentioned in the last slide, there's also energy efficiencies for large volumes. The vacuum system only uses water and steam utilities as opposed to other expensive cryogen liquids. In terms of operation, it's also a much safer operation. As you guys are aware, with any cryogens, you have to be careful to make sure that you have an oxygen sensor inside the room, as well as an exhaust fan, because if you don't, it obviously presents a risk for your operators. The other benefit is being scalable and flexible. It works on a wide range of products, batch sizes, and product types. With that said, I'd like to conclude my presentation, and I would like to thank you guys for attending.